Capasso.
Okay, thank you very much for the introduction. I'm honored to present this talk in the International Day of Light. And so the topic is flat optics, and I'm going to cover both the high-tech type of applications, such as meta lenses, talking even about the production, to the more researchy aspects, such as structure, like light and dark, using metasurfaces. These are the funding agencies. And this is just, I want to discuss that the main building block is the metasurface, which is a sub-wavelength spaced array of optical elements. So you can locally control the actual phase. And if you take the envelope of the wavelengths using Huygens Fresnel principle, you can predict, you can construct rather the wavefront in principle and arbitrary distance from the metasurface. In general, you can go beyond controlling the phase. You can control, of course, also the amplitude and the polarization. So the benefit of this approach from a technology point of view, it's lithographically defined. So that means you really can make flat optics in the sense of elements that can focus light, can manipulate light, using the same technology that is used to make in integrated circuits. From a lithographic point of view, this means deep UV lithography and also beyond, like EUV and so forth. And so this is on the technology side. And this, of course, opens tons of applications and high volumes. The key point from the physics is the unprecedented control of the dispersion. You see, these elements can be considered as tiny waveguides, and by changing, for example, in these pillars, the diameter, you can control the overlap factor with the incident light, so you can control the effective refractive index locally, point by point. And this adds a design element that simply is not available even in present-day diffractive optics, such as Fresnel optics, multi-level optics, and actually so forth. The advantage is you can overcome the limitation of conventional optics in terms of the aberration and achieve multifunctionality. It's a very interesting aspect. And this is a review article that we wrote a couple of years ago, basically. So this is the big vision of flat optics. Again, I want to stress that metasurfaces provide arbitrary control of the wavefront. They enable flat optics. And the key point is the middle bullet there, the same foundries, and this is happening as we speak, that manufacture camera sensors will also manufacture lenses using the same technology. So we are talking, and this is not in 5-10 years, it's going to start happening in a year or actually 2 from now. It's happening now in fact, though I can't say much on it, to achieve CMOS compatible flat optics for high volume markets. So we are talking here cell phones, laptops, and so forth, sensor for cars and so forth. And on the second part of my talk, which is generating arbitrary vector beams using metasurfaces, well beyond the capabilities of SLM. I don't have any particular application here in mind, but often happens you start with more basic type of research and you end up ultimately doing something useful. At least that's our hope in this area. And I want to stress, although I have very little time, to the importance of inverse design in the future. Whether as physicists we like it or not, it's immaterial. It will have a major impact on actual optics, and we have started to work in this area as well. So this is an example of a few years ago with my group, proved exactly the main point I said before, that using conventional deep UV lithography used to make chips, we fabricated lenses, the simplest possible lens made of glass, where you have about 160 million nanostructure per lens. It's diffraction limited. Basically, inherently, this has no spherical aberration, as you can see here from the right, and you have a nice, well-defined diffraction limited spot with a high strail ratio. So this immediately pointed to the unification in the future of two industry, integrated circuit and optics, and in fact, it got a lot of attention also among companies. So this is the latest. We had a challenge from DARPA, who has been funding my group for 5-6 years, to make the largest possible metal lens. So my people rose to this challenge and fabricated a 10 centimeters metal lens. And again, here visually, you can see the relative advantage compared to conventional commercial refractive optics. Here is our lens. This is Edmund Optics. And you can see what's the advantage. Well, there is a reduction in thickness by almost a factor of 50. There is more than a factor of 10 of reduction in actual weight, and there are other advantages as well. So this can have some interesting application for space, for example. So my group jumped on this opportunity. This is still work that is unpublished, ready to be submitted soon, and decided to mount it on an actual telescope on the roof of a building nearby. And of course, there is a filter to get rid of the background. And they did a simple test. How can this compare to conventional optics? So they decided to look at the nebula, the North American nebula. You can see here on the left with a metal lens. And this is comparison with the conventional refractive optics. So even though this is qualitative, and I don't want to particularly make too many claims, it's certainly indicative of the advantages of flat optics for application, including the scientific ones. And now I want to talk about metal lens. It was a spin-off from my group in 2016. And what we again saw the convergence of electronics and optics, integrated circuits and flat optics. So we got a head start. And right now we have 30 people. We are beyond the startup stage. We had a round B of investment recently. And a telling sign is some of the strategic investors that support metal lens. There is Intel. There is Applied Materials, there is 3M, and so forth. And so here really to target the high volume consumer electronics and automotive market, okay? And the central idea is to be fabless. We do the design, the actual prototype, but then the big foundries are going to make this because they're already the technology platform. You see, that is the key point. So this shows the existence proof, okay? The way you do the electronics, basically you have an electronic design file, you enter it in your lithographic system, and it spits out this 12-inch wafer of silicon and so forth. In this case, instead, you have an optical design file, and this is a demonstration of a generation of a 12-inch wafer. This is of glass with 10,000 amorphous silicon meta-optics for applications such as depth sensing, face recognition, and so forth. So this is very significant. This was done, in fact, in a major semiconductor company. And so it's, in a sense, more than an existence proof. It's actually here. And I want to mention one of the advantages of doing flat optics. Take a conventional sensor here to the left. It's made up of multiple plastic lenses. You see there are different materials and different shapes. And the alignment is very critical. And it's significantly thicker than if you use flat optics. The key point here, the intensity fades away from the center. That's physics. There is no way around with refractive optics. As you move away from the center, the light travels for a longer distance, so the intensity is actually less towards the edge of the sensor. But you can make, with a very simple system like this, just an aperture and a single meta-optics, you can achieve telecentricity. Means basically in intensity that is practically uniform up to the edges. You see here two pictures of one with a full plastic conventional contact sensor here, and one with actually metal lens. And you see not only the greater uniformity, but also the higher brightness, so increase signal to noise. So in fact, in last year, Metalens and ST Microelectronics, that is a major company that makes chips and delivers consumer electronic product, went into an agreement to have optical metasurfaces for vision. This stuff is entering the system right now. Unfortunately, because there's a lot of proprietary type of information, I can't be more specific than this, but I can only say something, that within 2 years, you will see meta lenses. You will see big foundries entering in this and delivering meta lenses in actual cell phones and other systems such as laptops and so forth. I think it's an irreversible process for the reason that I tried to highlight before. Now I want to move more to the research part. You see, these are single wavelength lenses. You might say, why single wavelengths? Well, if you want to do depth sensing, face recognition, you don't need an achromatic broadband lens. You can just focus. In fact, the lenses I showed you before were designed for the wavelengths of vertical cavity surface emitting laser that are part of the, for example, the face recognition system in the actual iPhones. Okay, so it's a wavelengths around 900 nanometer. But so there is a high volume market just for these, what I call single wavelengths meta lenses. But of course, we are ambitious. We said, how about trying to make a broadband meta lens, much simpler than conventional one? If you try to make a broadband achromatic lens, there is no way to do it with a single refractive lens. That's just the physics. So you have to use multiple refractive lenses and different materials, so they are bulky and so forth. So in this work, we showed that with a single meta lens, essentially using dispersion engineering, we can achieve achromatic focusing across the visible, as you can see here. And in fact, by designing the dispersion, these meta optics here, we can achieve either a meta lens that acts as a refractive lens, meaning that it focuses the shorter wavelengths at shorter distances, or as a diffractive lens, as you see here on the right, which does tighter focusing, shorter focusing length at longer wavelengths, or in this case, an achromatic lens. So you can literally engineer the behavior of the focal lens with frequency using this type of diffractive optics, using meta optics. You can even do white light focusing and so forth. The limitation of this strategy so far is the difficulty to make these lenses really large. So we managed to do this only for 100 micron. We should be able to overcome this, but we are not quite there yet. So we decide, let's take a step back. Why don't we make an RGB lens, a meta lens that focuses the primary colors, red, blue, and green, for applications such as virtual reality? So for that, we decide to do inverse design, because you have to make lenses that are realistic diameters, like 1 centimeter. So inverse design is sort of simple conceptually. What you determine an objective function. For example, maximize the intensity of light at a certain distance. You start from a random design, and then you do a series of loops where you calculate what your target is, and by readjusting these actual structure here, so a series of loops, you can converge arbitrarily close to what your objective function is. And this is called inverse design. In particular, this is called a joint optimization method. This was done in collaboration with a group of Steve Johnson at MIT. And these are the results summarized here. 1 centimeter. This is titanium dioxide. Like the previous one, for the visible, we use transparent titanium dioxide. And you see we're able to achieve essentially the same focal lengths with only changes of 0.03% of the design wavelengths as we move from the blue to the green to the actual red. So we started to play a bit. We made a VR setup, and we showed we could make binary virtual reality images with well-resolved pixel, grayscale via images, and color mixing, and also did a nice movie. Okay, so So now what I want to move is to the latest thing, this work that we published in Science with a group of Martin Schulz. And the idea is, we said, can we make an extreme UV metal lens? You know, extreme UV is the frontier of technology, but it's also a frontier of science. And this deals with this famous field of attosecond, of achieving attosecond pulses with high harmonic generation. So high harmonic generation, this is a system that we used. Our collaborators in University of Graz use an IR driving laser, and this is a well-known, but I want to quickly summarize. So you focus this in an argon-filled tube, and you generate a series of, you generate 1 attosecond pulse every half cycle of the driving laser. So you can create many harmonics. Odd are harmonics of the driving frequency. So now here comes a neat idea that my postdoc, Marcus Osiander, who now in fact works at University of Graz, had. It's really cool. The idea, he said, how can I focus now ultraviolet light, this extreme UV light? So I want to use a platform of silicon. And the interesting thing is that in the wavelength range around, tens of nanometers, the actual refractive index of silicon is less than that of vacuum. So it's less than actual unity. Okay, so you can use the vacuum. We call this vacuum guiding. Vacuum, we are not saying air. You cannot use air when you work with extreme UV, right? So these are lenses that are immersed in actual vacuum, okay, and they focus light by where the guiding is provided by the empty part. That's the innovative aspect. And because of this refractive index of silicon, which is negative in this wavelength range, well, what's the point? Is it worth it? So my group did simulation of a metasurface lens in the extreme UV, as opposed to what's used conventional technology. You see, there is no conventional optics for EUV. You either use mirror or you can use Fresnel zone plates. You see, when you use Fresnel zone plate, there's a lot of extra stuff you really don't want. Look here in a transverse direction, but if you use a metasurface, you can clean up the focal region significantly. So basically, what my group did is make this, and this was really a tremendous amount of work over 2 years period, managed to make these ultra-thin membranes, holy membranes. And the driving force of this technology is Marina Mereska. She's a researcher in my group, and also Daniel Lim. And so, and then our colleagues probed these, they focused light essentially with this metal lens here. They were interested in particular the 21st harmonic of the driving field, which is lambda equal 50 nanometer. And basically now, how can you measure the focal property of this? You cannot use conventional optics. So we resorted to the traditional method of a knife edge. You move a knife edge, a razor blade, basically, both perpendicular to the focal line, to the axis, or parallel here. And by watching the intensity profile as it changes when you do this, you can actually, that's exactly done here, through these curves here, where you move laterally and up and down, you can determine the actual beam waves, and it's close to what you calculate. So this is the beginning, I think, of an exciting area of research. The last part of my talk is to talk about optical singularities of light. What is a singularity? A singularity is, it occurs when a parameter is not defined. For example, north and south pole, you cannot define the longitude. So that's a so-called coordinate singularity. We all know about gravitational singularities. And well known in optics are the so-called optical singularity due to vortex. You can create a wavefront that spirals around the propagation direction. There's a helical wavefront. And you create optical vortices where the intensity at the center is zero and the phase is undefined. So these are on-axis line singularity on a straight line. So we've asked the most general question: can we create two-dimensional singularity, sheets of dark where the phase is undefined, or zero-dimensional singularity, sort of dark spots, okay? So this is how we formulated in general the question of phase singularity. It's about structuring dark, right? Of course, you can describe the electromagnetic field as a sum of a real part and an imaginary part. It's a complex field. You have amplitude and phase. And the intersection of the real and imaginary part, you set it, which is equal to 0, and gives the singularity. And this singular region can be either a spot, can be a line, circular line, a straight line, as I said before, or a sheet. So we focus on the question, can we create a dark sheet of light? That's a very interesting physically. It might even have some application, to study defects in materials and so forth. I think quite exciting possibility, stress tomography and so forth. So the technique, there's a lot of simulation here, and I will slip it literally under the rug because of time. But the recipe to create the sheet singularity is you specify what is your desired sheet, okay, the target sheet, and then you want to maximize the phase gradient orthogonal to the design sheet. And this was published recently, a year ago, in Nature Communication. And so my student decided, let's make a heart shape singularity, singular region. This is a singular surface. And once we create it, how are we going to look at? Well, we have to create an optical system so that we can translate along the propagation direction and see if we achieve. In fact, I'll show you the full metasurface here. This was used titanium dioxide at visible wavelengths. And you can see here that this is a particular cross-section. Indeed, we have a singular region here. Here's the phase, simulated phase, and this is the intensity. Now, of course, there is still a background, but it's unquestionable that for the parameters that we designed this, we actually do achieve the predicted heart shape, cross-section of this heart-shaped surfaces. So, in fact, this is the optical system. And as we translate this with this tube lens here, you can see there is still a lot of background. So we are not quite there yet, but we are close to really, we have to manage to suppress this actual background. But it's basically, we have already, in the sense of the shape and where it occurs, for which parameters and at what distance, we are already there. And I would say that the pioneering theoretical work on singular optics was done by Michael Berry in a very famous paper a few years ago with NIE, NYE. And the next thing we decided, why not to make dark singularities, basically spots of light. You see dark regions here that are singular, and particularly an array of equally spaced singularity. Why? We want to make a blue detuned trap. You see the famous traps, optical trap, for which Ashkin a few years ago got the Nobel Prize in physics. They are red-shifted trap. Basically, you have an atom, you have a colloid, you want to trap it in the focus of a lens, you want to redshift the laser wavelengths towards the red side, so then the particle can be shown to be attracted to the focus. And this is the famous gradient force. But it's well known that you could make a dark trap, only they are not so much developed so far, so that when you are blue shifted, the particle, the colloid, the atom, whatever, is attracted towards the dark region. So that was our goal, our vision. So for that, we use inverse design, where we dictated the objective function. So it's essentially to have creation of singular point and maximizing the actual phase gradient and enforcing trap uniformity, right, where you see the arrows here. So that's the goal. And in fact, technology that Daniel Lim developed is really, you can see, even visually beautiful, as you can see from here. You can see this phase basically this creates the phase map necessary to achieve an array of dark traps. And again, titanium dioxide is a platform that we use routinely for the visible. This was done, in fact, for green light. And these are the experimental results. These are the numerical simulation here, okay? Yes, we have the numerical simulation. Then we have the experiment where we take both a horizontal X cut and a horizontal Y cut. So you can see good trap uniformity. And here actually is the intensity, the transverse XY cut. You can see here clearly where I'm pointing my cursor here, the singular region. So then the last topic is, how about structuring light along the propagation direction? Can we achieve a beta surface so that as light propagates, the polarization changes along the axis, or the vorticity? You create optical vortices that change along the propagation direction. Can you play fancy games such as I change the incident polarization from elliptical this way to the perpendicular ellipsis? I can get a different evolution of the vortex from low to high or high to low in a somewhat arbitrary way by design, or create then something that combines this with this. I want to dispose of an objection here. First thing you can think, Federico, you are violating spin and angular momentum conservation because they cannot change in actual vacuum along the propagation direction. Correct. The statement I made is valid around the optical axis. So around the optical axis, if you do simulation, the experiment, you do see these vortices that change. You do see the polarization that changes. But you are only looking at the center. If you actually integrate the spin and the optical angular momentum density in the transverse plane, you see that as you propagate along, these are conserved quantities. So we are not violating any physical law, but can achieve the structuring of light in an angular region that is not negligible. We have gone up to 5-10 degrees, okay, over a significant distance of up to several centimeters. Can this be useful? Maybe. Micromanipulation of color, maybe for communication. I don't know. It's just premature. So far, we're just having fun. Okay, so this is what was the first goal, to essentially, achieve a virtual analyzer. And to be useful, the beam has to be collimated. So we decided to create bezel-like beams of varying polarization along the optical axis. So for that, there is a lot of theory behind, developed in this paper, science paper called matrix Fourier optics. Is a powerful generalization of Fourier optics that involves the vector aspects of light, the polarization. So essentially, the metasurface creates a superposition of pencil-like, so these are collimated bezel beams with different cone angles and different polarization. So it creates an interference, and as the light propagates, this superposition evolves in such a way to change the polarization point by point near the axis. Okay, so again, the bezel beams are because you want to try to maintain the beam as tight as possible near the optical axis. And does this work? Yes. This really acts as a virtual analyzer. We use a 4F optical system, translated it, and you see for incident X polarization, it's as if you had a virtual polarizer along the propagation direction. This is Z. And as you move along, it's as if you are rotating, the polarized intensity fades away for one polarization. For the perpendicular polarization, you get the opposite behavior. So it's really kind of neat. The next thing, can we do what I said before? For an incident polarization, change the optical angular momentum as it propagates near the optical axis, the light, and when we hit it with the perpendicular polarization, achieve a different behavior by design, where we change from this vortex to the other. The physics behind it sort of related to what I said before. Well, now it's a bit more complex, okay? What does the metasurface create? It essentially creates what we call optical angular momentum combs. These are combs. These are the vectorial components of light that are equally spaced in the spatial frequency domain. What is spatial frequency? Is the component of the wave vector along the propagation direction. So it creates these combs. They propagate. In propagating, they interfere, and by design in such a way that at one end it looks like a vortex with a optical angular momentum of L1, and at the other end, this. So it's all a game of constructive and destructive interference, okay? And so that's the point. And so my group designed these nice metasurfaces. Here you can see they even look always visually nice, which is kind of neat. And we use this system here is a 4F system. So we reproduce here, okay, near the 4F, what's after the actual metasurface. And we can control, we can design the incident, change the incident polarization by using a half-wave plate and a quarter-wave plate. In this case, we want elliptical. And then we want to measure the spiral, right? How many arms of the spiral? This gives the optical angular momentum. So this is a known technique. We have to divert the original beam, say Gaussian beam. Okay, no, actually, yes, the Gaussian beam. Here it becomes a Bessel beam here, and interfere it with the generated beam. And the interference pattern will actually give you this spiral structure. So does it work? Yes, it works actually. I hope I can start this movie. I had problems. No, I had problems. Oh, yes. So you can see here we are stepping the camera along the Z direction near the 4F, the second focus. And you can see, we see this evolution. L plus is this polarization here, elliptical. And then this instead, when we hit it with the other polarization, you see, we actually see the opposite. We have a different behavior. And this shows the actual snapshot of what the actual movie shows. So we have a very good demonstration. So in summary, we can create structure light, structure dark with metasurface. As I said, there are potentially some very interesting applications. You see, the dark is not diffraction limited. This is one of the reasons why they gave the Nobel Prize years ago in chemistry also to actually Stefan Hell. He used this, right? So our idea here is to use this structure dark to look at, for example, defects in materials that are much smaller than the diffraction limited, for example, point defects. So maybe we can do some kind of stress tomography using structure dark. This is a bit a long-term vision, but I think it has some scientific merit to think about in this direction. And this now allows me to get to the end of my talk. And basically, I showed you, I hope, the significance and potential of flat optics based on metasurfaces. Technologically, again, the convergence of what the foundries do with semiconductor technology and the fact that you can use semiconductor technology to do optics is going to be game changers for high volume market. I'm not stating, of course, there'll always be plenty of application for refractive optics. I'm talking here of the space of consumer electronics market and so forth, and possibly, other application as well. I showed you some space application, so there are the multifunctionality. Well, I showed you some example multifunctionality. You can design flat optics to do any kind of manipulation of the waveform that you actually want. So you can generate arbitrary vector beams, and then the importance of inverse design and eventually co-design of hardware and software. So I believe that AI will have a very significant impact on optical design. This work could not have been done without some fantastic group of students, postdoc and external collaborator. I mentioned already the group of Martin Schulz, the work we have been doing with my group on EUV lenses, the group of Professor Steve Johnson at MIT, or Professor Doug Werner at Penn State University. I didn't have literally time to talk about the work with Corning, but we have done interesting work on essentially making Dmax metasurfaces to couple light to multi-core fiber, to few mode fiber, and so forth for spatial division multiplexing. And he is the group leader here at Corning of this effort. And I want to highlight Rob Devlin, who is the CEO of Metalens, Marina Mereska, I mentioned, J1 O, who did a lot of work in various aspects, Junsu Park driving the large lens work. I mentioned Marcus in the work on EUV, Zhao Yi on the work on RGB metal lenses. Arman Amirsan is a very interesting young student who works in different topics. He was instrumental in the space application of metal lens. I mentioned Daniel Lim. Finally, I want to mention Christina Benea Kelmus, who spent 2 years in my group. She's a professor at EPFL, and she contributed to many aspects of the actual work, including active metasurfaces. Because of time, I couldn't cover. So again, thank you for this invitation, and I'm happy to answer questions.